Okay, this is a quick video about what goes on in a basic circuit loop. The main idea is you always have some battery, which is a source of voltage, and maybe you've come across the word voltage before. Maybe you've heard it's synonymous with electric potential, and even though it seems like it's something very different in circuits, I'll get to it a little bit later, it really does mean the same thing you've been talking about this whole time. And then, okay, we've got a couple resistors, which are not necessarily the same value. It's about as simple as you can get when it comes to circuits. So what's going on? The battery is really a positive plate and a negative plate. Now, there's some sort of magic inside a battery that keeps the positive plate positive and the negative plate negative. We won't talk about how that happens here. Maybe we'll do that in another video. But the key idea is that the positive plate pushes positive charges away from it, and the negative plate pulls positive charges toward it so that it looks something like this. All around the circuit, you've got positive charges moving. Now, okay, I know in real life it's actually the electrons moving, but we decided a long time ago that we would just say that the positive charges move to the left instead of negative charges moving to the right. These turn out to be mathematically equivalent, and so no one's ever bothered to fix it, and it's just convenient to say that the positive charges are the ones doing the movement. So at any rate, the positive plate pushes these positive charges clockwise around this particular circuit. Well, what happens? What happens is the battery's job is to give each of these positive charges energy. How does it do that? Well, positive plate creates an electric field. An electric field exerts a force on this guy. That force accelerates that guy. The job of the resistors is to steal the energy that the battery is given. Notice that the voltage across each resistor, this is Ohm's law, by the way, notice that minus sign is there because the voltage drops when you go across a resistor. Why does the voltage drop? The voltage drops because the particle is losing energy. How is it losing energy? Well, imagine here's your particle, and there's these big clumpy atoms inside of the resistor. Well, this particle goes and tries to make its way through the resistor, but it's difficult and it has lots of collisions, and each one of those collisions slows the particle down. You could think the particle would experience some change in kinetic energy as it went through the resistor if it were not for the fact that the battery keeps pushing it forward. So this is a steady state circuit. And what that means is not necessarily that nothing's moving, but that after a bit of tumultuous beginning, all of it has kind of settled out, and exactly the amount of energy that the resistors want to steal, the battery is supplying to the charges. And you might say, wait a minute, the battery's all the way over here. Hasn't it already given the charge the energy, and shouldn't the charge slow down when it gets here? Okay, that's a fair point, and this model that we're looking at now is actually a bit simpler than what's really going on. What's really going on is there's all sorts of pockets of accumulated charge in various places around this circuit that are driving things around the circuit. We're not going to get into that here, though, because it turns out you don't need to. You can just pretend that all of the acceleration happens in the battery and all of the deceleration happens in the resistors, and that somehow those conspire to make all these charges move at a constant speed. Okay, so enough of that. Let's just see what this actually, how do you analyze this, right? Okay, so you've got your battery, you've got your resistors, and we keep throwing around this word voltage. Well, what does voltage mean? We could talk about the voltage between A and B. That would be something like V, BA, for example, which might be the voltage at B minus the voltage at A. What does that mean? Well, if you remember, when we talked about electric potential and voltage earlier, we talked about topographical maps. And in fact, these little lines on a topographical map are places where the height is constant. So this map has mountains and it has valleys, and where these lines are close together, it means that the height is changing very quickly. And where they're far apart, it means that the height is not changing very quickly. The key thing, though, is that so long as you ride this line, so long as you don't deviate from this line, your height will always be the same. Remember that your height is related to your gravitational potential energy, MGH. So when we say your height is the same, it's really the same as saying your gravitational potential energy is the same. Well, remember that electric potential energy or voltage, these are the same thing, is related to electrical potential energy, right? So just as your height changing affects your gravitational potential energy, your voltage changing affects your electrical potential energy. Notice I put an E here because it's things that have the charge of an electron moving around the circuit. Really, it's electrons moving around the circuit, but remember, we're pretending positive charges that have the charge of an electron move around a circuit. Well, the key idea here is that there is a voltage at A, just like there is a height on this line. There's a height on this line A. That has a particular height right here. Well, this also has a particular voltage right here. And if I wanted to know the difference in height between 2 points, okay, well, I'd measure the difference in height. I'd count the number of lines or something, and that would tell me that. And if I want to know the difference in voltage between these 2 points, A and B, I would look at what's going on between them and I would add it up. In this case, what's going on between them is the battery. So I would expect the difference in potential between A and B to be equal to the battery. So VAB should be equal to delta V, this thing over here that we wrote, the potential of the battery. Okay? Here's a way to think of it. Let's say that I'm starting at A. A is at a particular height, just like I can say there's a particular height at that point A. If I want to move to B, I need to go across the battery. What does that look like? That looks like going in the clockwise direction. If I go across the battery has now increased the voltage of my particle, meaning I gave it some extra energy. Now I'm at the point B. Well, what happens after B? I go through resistor 1. What is resistor 1's job? It's to decrease my energy or shrink my height. That looks something like this. Notice that I'm flat this whole time. This is, in some sense, also an equipotential. In other words, from here to here, there's nothing going on here, and this is all at the same voltage. All at the same voltage. Okay? So after I go through C, if I want to go, I don't know, say back to A, I've got to now go through that resistor. So if I do that, I go down again. And I don't think it'll surprise you to know that the height here is exactly the same as the height here. That's why I bothered bringing up this whole topographical map thing. It's like starting at a particular place, going on a little journey, but then returning to the original place you were. The height has to be the same. Now, that seems trivial, but it actually is a very useful calculational tool. What do I mean by that? Well, I can label all of the heights that I go up and down. So here's the battery, it's delta V. Here's the voltage across one resistor, it's IR1. Here's the voltage across another resistor, IR2. And by the way, I could keep this thing going on and on forever, just circle after circle after circle. Now, if I add up all of these height differences, they ought to add up to 0. Why? I start at A, I end at A. All these going up and coming down, they all have to add up to 0. This, by the way, is called a Kirchoff loop, and this law, which we're kind of deriving right now, is called Kirchoff's law. But Kirchoff's law is really nothing more than the observation that if you start at A and you end at A, you can't have changed your energy. It has to all add up to 0, whatever you do in between. Okay, so whatever, you do a little bit of algebra, and now you can solve for the current in this circuit. If you notice something, if you've seen this before, you may know that for a series circuit, you may know that Req equals R1 plus R2, and it seems like actually we've kind of just derived that. In other words, there's some equivalent resistance that the battery sees here, and it's equal to R1, R2. So as far as the battery is concerned, it's not hooked up to 2 resistors. It's hooked up to 1 resistor, and it has resistance of that. The rules for a parallel circuit, by the way, also come from doing Kirchoff loops. The circuit looks a little bit more complicated, and we do the algebra a little bit more differently. And that's probably a subject for another video, but the idea is the same. They're not mysterious. They simply come from this really rather stupid idea that the electrical potential energy at A is well defined, and that if you go somewhere and you come back to A, you have to have the same energy you had before. We are going to do lots and lots of loops like this with more complicated systems, but this is the basic idea. Okay, hopefully this was more helpful than confusing.